Let's try an optimization problem. So here a home improvement store is designing a new bucket to sell, and the bucket is in the shape of a cylinder. So the volume is given by this nice formula pi r squared h, where r is the bucket's radius and h is the bucket's height, both measured in feet. So just to give a picture, you have a bucket and we have some radius r, and the height here is exactly h. Let's read on. Since the bucket does not have a top, so I guess the bottom is filled in, the sides are filled in, but the top, you want to be able to throw things in, I guess. So the top is open. So the surface area, if you know equation of a surface area of a cylinder, say, you see that it's A equals to 2 pi RH plus pi r squared. Usually in the equation for surface area of a cylinder, you have 2 pi r squared, not just pi r squared, but the thing is, we're not counting the area on top. That's the reason we just have 1 pi r squared here, in case you're interested. And now the store has decided that the new bucket should have a volume of exactly 1 cubic foot. So we know this entire thing should be exactly equal to 1. And we now want to find the dimensions of the bucket. So given that the volume is 1, that will minimize. So let me highlight this. This is really important. This is what we want to do. We want to minimize the surface area of the bucket. And of course, we want to use calculus to find and justify the answer and show enough evidence to show that we actually found the minimum, not just some critical point that might be a maximum or neither or something like that. We want to actually justify that we know what the minimum exactly is. Okay, so how do we start? Well, whenever you're given a optimization problem, this is really a global max or min problem. And whenever you're trying to figure out how to globally maximize or globally minimize, there are two things you need to figure out from the get-go. So the first thing is, what function are we minimizing or maximizing? So the second question to ask is, the maximization and minimization, on what interval is this happening? And the interval matters a lot. For example, if I consider maybe a graph of something like this, maybe this is 0, and maybe I can look at a function that's increasing up to say infinity. And now here, if I ask you what is the maximum from say like 0 to 5, well, the maximum is really easy to find. Here the global maximum on this interval, on the closed interval from 0 to 5, is certainly here, right? But if I change the interval, rather than going from 0 to 5 to say maybe 0 to infinity, in that case, do we have a maximum? No. The function is increasing to infinity. So now the answer is that the maximum does not exist. So depending on the interval, even if our function is the same, the maximum changes. So figuring out what interval in this realistic context that we want to really work with, this is a really important step in the optimization process. So make sure we figure out the function and the interval. So what are we doing here? Well, we know we are minimizing the surface area, and they tell us the equation for the surface area. So we know we're minimizing 2 pi RH plus pi r squared. But now, before we get to the question of the interval, there's actually one more point I want to make. Because so far we're in a single variable calculus. This is a calculus 1 class. Really, we only know how to minimize or maximize function with exactly one variable. And what is the problem here? Well, we have two variables. We have radius and height. So if we have two variables, you don't know how to differentiate it, at least at this point. So we really don't know how to minimize this. So what we have to do is we gotta first force this function to have exactly one variable. And how can we do that? Well, they gave us some information that the volume, this pi r squared h is 1. So let me write that down. Pi r squared h is 1, and this is going to allow us to get rid of one of the variable. For example, I think the easiest way is we can solve for h here. We can get 1 over pi r squared. You can also solve for r, but then you have to take square root and things are going to get messy. So I think it's easier to solve for h. So h is 1 over pi r squared, so I can now plug it into h right here. So when I plug this into h right here, now h disappears and everything is in terms of r. So it's like 2 pi r times 1 over pi r squared plus pi r squared. I guess you can simplify this a little, like pi's cancel out, r and r squared cancel out a little bit to leave just 1 r in the denominator. So we get 2 over r plus pi r squared. And now we see that this function has exactly 1 r. So let's call this A of R for A for the surface area, I guess. So that's I guess the first step. You want to make sure you want to write down what you want to maximize or minimize. If it has more than one variable, you want to use the information given to you to get rid of some variable until we just have a function of one variable. So we have done step 1. We found something to minimize. And now the step 2 is to figure out what interval are we reasonably dealing with. So here our function is in terms of the radius r. So the question is, what should be the interval corresponding to radius r? Well, radius r, I guess the most natural one is it can really be anywhere between 0 and infinity. Negative radius does not make sense. And I guess like maybe one thing that might be confusing is, do we include 0? So write including 0 to infinity, or do we exclude 0 and write the open parenthesis here? And I think here you really want to exclude it. I guess one reason that's not as important is that when radius is 0, then you might say, I mean, the can isn't really a can. Like if the radius is 0, then you only get like a one-dimensional line. So maybe that's something that you're worried about. But I guess like usually in mathematics, when things are degenerate, like when everything is collapsing one dimension lower, usually we're okay with that. So that's not as big of a problem mathematically. I guess realistically, maybe it is a bit of a problem and you don't want to include it. But a more serious issue here is that radius really cannot be 0 in order for this condition given to us to be true. So we know this thing is true 100% because the volume they tell us is 1 cubic foot. But when radius is 0, then we get 0 on the left hand side. So this thing just cannot possibly happen when radius is 0. So we see that r equals to 0 just cannot happen according to this formula. So we know the radius should go from 0 to infinity. So to summarize, what we want to do is we want to minimize this a of r, 2 over r plus pi r squared on 0 infinity. That's what it comes down to. And now how do you find the global minima of some function on some interval? I actually have a video on this where I go through the global minimization process pretty thoroughly. So I will not spend too much effort into diving into every detail. So just to give a quick outline of how you do this, first you want to find the critical points. And in order to find critical points, we differentiate it. So a prime of r. So 2 over r, when you differentiate it, I guess if you're having a bit of trouble, you may want to write it as 2 times r to the negative 1. And then you can use the power rule. This negative 1 drops down. You subtract 1 from the exponent. So you get negative 2 r to the negative 2. And I guess r to the negative 2 is really dividing by r squared. Whereas when I differentiate plus pi r squared, I get plus 2 pi r. And for critical points, I want to look at where a prime of r is undefined, it does not exist, or where a prime of r is 0. So where is a prime of r does not exist? Well, looking at this, the way that you can make this undefined is when you're dividing by 0. So you see that r equals to 0 is one way, but here the only critical points we care about are critical points in this interval from 0 to infinity, not including 0. So r equals to 0, it's really not in the interval that we care about. So we can just throw this out. We don't need to worry about it. What about when a prime of r is 0? And here what we really want to do is we want to write this entire thing as something divided by something. Because once we write it as just one fraction, we can easily see where it's 0 by just looking at where the numerator is 0. Because that's when the fraction is 0. And how can we combine these two things into one fraction? Well, you just gotta make them have the same denominator. So here what I can do is I can write 2 pi r as 2 pi r over r squared. I gotta multiply by r squared to the top. So let's write it as 2 pi r cubed over r squared. And now I can add them up, negative 2 plus 2 pi r cubed divided by r squared. And now we can easily find the critical point where it's 0 by looking at where the numerator is 0. So that's what we want. So we want to look at where 2 pi r cubed minus 2 is 0. And this exactly happens when I move 2 to the other side. Divide by 2 pi, you get r cubed is equal to 2 over 2 pi, or just 1 over pi. And now I can raise both sides by like 1/3 the power to cancel out this 3. So we're going to get r is equal to 1 over pi raised to 1/3. And to finish, And to finish, how do you find global max and min? Well, we find global max and min by comparing function values or limit that we care about. So surely we need to care about, so we want to compare a at critical points, say 1 over pi to the 1/3. And we also want to look at the endpoints. So here, for the left-hand point of 0, we cannot do a of 0 because we're not including 0. So what we want to do is we want to take the limit at 0. And since we only have things to the right of 0 in this interval, we can approach 0 from the right. So we want to take a look at limit as r goes to 0 from the right of a of r. And finally, the last thing we want to look at is right endpoint of infinity. Here we have no choice. We can only approach it using limit. So we have limit as r going to infinity of a of r here. So let's evaluate each one. So for the first one, what happens when I plug in 1 over pi to the 1/3 into this? Well, when you plug in 1 over pi to the 1/3 here, pi to the 1/3 is actually going to go up to the numerator. So we get 2 pi to the 1/3 plus pi times r squared. When I square this, I'm going to get times 1 over pi to the 2/3, right? I just raised this by 2. And I guess we can simplify this if we want. Pi divided by pi to the 2/3 is pi to the 1/3. So we have 3 times pi to the 1/3 for the first one. What about the second one? Limit as r goes to 0 of a of r. Well, looking at this, when r goes to 0, this thing is going to go to 0, right? Whereas 2 over r, as r is going to 0, so imagine plugging in r equals to 0.1, 0.01, 0.001. So what happens when we plug in r equals to 0.1, 0.01, 0.001? Well, you're dividing by something small. So 2 over something small, that's going to be really big. And you're dealing with positive numbers here because you're approaching 0 from the right. So this limit is going to be positive infinity. Finally, what's the limit as r goes to infinity of a of r? Well, let's again go back up. When r goes to infinity, you're doing 2 divided by million, billion, trillion. So this part now goes to 0. Whereas pi r squared, as r is blowing up, pi r squared is going to blow up towards infinity. So we see that here this thing is infinity as well. So we want to find global minimum here. You're trying to minimize. So which one is the smallest? Well, the smallest is happening. I guess we didn't even really need to calculate this. We know this thing is smaller among these three choices, certainly. So here the global minimum is happening at 1 over pi to the 1/3. So our conclusion is that the global min at radius is 1 over pi to the 1/3, but we are not done because let's read the question carefully. What do we want to find? We want to find the dimensions of the bucket that will minimize the surface area. So we have found the radius minimizing the surface area. Now what about the height? Well, the height, we know the relationship between height and radius from right here. Remember, this thing is coming from the volume equaling 1. But we know from this equation, so h is 1 over pi r squared. So we know h is 1 over pi r squared. So we can also find the height. So we know the full dimension of the bucket. And that's 1 over pi times, when I square this, it's pi to the 2/3. And pi divided by pi to the 2/3 is pi to the 1/3. So we get 1 over pi to the 1/3. So we see pretty remarkably the global minimum is happening when radius is 1 over pi to the 1/3 and when the height is also 1 over pi to the 1/3.